Good morning. It's the physics video lecture once again. That's Physics 105A, video lecture 25. We're in the middle of the Fourier series section. Gotta grab some pens here. So, we're going to do a couple of things. We're going to review the summation of these series, and I'll give you one more problem. Then I'm going to develop a bunch of formulas for different intervals and stuff. You'll see, it's really just a bunch of bookkeeping. But then we're going to go into the whole meaning of this Fourier business that I think you'll find very, very interesting. So first things first, let's just do one more example and we'll have the formulas on the board. So we now know that we can expand a function, and I'm going to draw the one right away that we want for the homework. So minus pi to pi, and let's let that be 1. Okay. So we want to expand this function here in a Fourier series, and we know it can be done with the form of f of x being the sum of c sub k e to the I kx, all integers, and these c sub k's be 1 over 2 pi minus pi to pi f of x e to the minus I kx dx. So this will be a good last one to do. I should even point out, you can, so this is homework. We want to get the Fourier series for this thing here. It may or may not be easier to use the real series because we have an even function here. Okay, all of the b sub k's will vanish, but do it either way. So I'm going to say, because the final result will be the same. You go to the complex or the real version, this is the real function, the final result will be a sum of cosines. But, so let's just write here, construct Fourier series. And just for fun, evaluate at x equals 0, you should then get another infinite series representation involving the number pi, and find an expression for pi. So that's what we want to do. We have these two tasks here, and we need to get a hold of that function. So what do we have here? F of x is equal to, so for the left half of it, we could use the point slope idea. And for the right half, we can also use the point slope idea. So the first thing you have to do is get the equation of this line, okay? Get the equation of this line for minus pi to pi. So minus pi less or equal to x less than 0. And then you have to get the equation of this line, just point slope formula, make sure you got it right. And that'll be for 0 less or equal to x less than or equal to pi. So yeah, once you've found the expression for f of x, it's a straight line. So looks like you're going to have to do an integration by parts, whichever formulation you use. But then this is useful because this is going to be a sawtooth type of wave, okay? And I'm going to talk about time instead of position Fourier series in a moment, so you'd even be able to turn that into a time, a function of time, and then that would be a sawtooth type of wave. And you could generalize easily by, instead of having it equal 1, you could have it equal any positive constant. Those are all just details. So that's how you get started. Find the equation of the line and the other line, and then go ahead and evaluate your coefficients. Good, then we'll be done with that. And of course, since you've got that periodicity, this is what you really have, right? You've got this function. And you'll see a couple of interesting things. So this is a good assignment. Good, the next thing I'm going to do builds on this, and is really just some bookkeeping. So we'll do it directly underneath these formulas on this next board. So here's the question. Suppose instead of a function that goes from minus pi to pi, we have a function that goes from minus L to L, or some other symmetric interval. So next, we're going to have, in fact, let's just draw it, minus L to L. And we've got some f of x. So how do we expand that? We should just be able to do a little transformation of these formulas, and we will. And they will also carry over to the real formulas. I'll say a little bit more about that when we're done here. So what we're looking for is f of x. The complex ones are just the easiest to work with for theoretical purposes. Good. F of x, we're just doing a sum over these intervals again. C sub k. So what's going on here is that we have a periodicity where we go I, k, x equals pi, k is an integer, so we need that 2 pi periodicity over the entire interval, and we need that here too. So what we're saying is it's got to be e to the I, k, pi over L times x. And now when x is equal to L, we're at the right end of the similar interval up there. So what are the c sub k's going to be? Leave a little space there. 1 over 2 pi is the width of the entire interval. It's going to be 1 over 2L. Like I said, this is just bookkeeping. Minus L to L. E to the minus I k, same thing. Pi over L x dx. So that just adds another little complication. And for all our theoretical discussions, we're just going to use these because they're the simplest. But that's all it takes to go from a minus L to L. And suppose we have, so we could put a label on this. Suppose we have functions of time, so f of t, and then it might be good to have a capital T as the total interval. Makes sense, right? Because then you'd have a periodic function with period uppercase T, and then you just have it displayed symmetrically along that interval, and it would, continue indefinitely to the left and right. In fact, our sawtooth wave as a function of time might just be that if we're in the electronics lab. So, what do we do here? I wanted to stack these so I'll work right under here. So here we're going to have f of t is equal to sum over c sub k minus infinity to plus infinity, and we're going to have an e to the I k. K is just the whole number index, right? So instead of pi over L, we're going to have pi of 2 pi. 2 pi over capital T times T. And we just change the name of L to T over 2. Okay, so that's what happens. So that's important. And our coefficients are going to be 1 over the period minus plus t over 2 f of t e to the minus I k 2 pi over t times t dt. Okay, you see, you can just invent these things. This is what you really have to remember. If we're going to be coming back to this. So yeah, this, like I said, is just bookkeeping, but you can see the obvious applications. And you might want to just take a single page and assemble everything we've done just in terms of formulas. You'll have a reference. Okay? You'll have a reference. Good, so I won't call that a homework. This one definitely is a good last homework problem on calculating one of these things. Okay. So I'm going to do a couple of things now. One thing here, let's just focus on this for the moment, because I'm going to leave this, but we're going to come back to this in the future. This form, we could also do the one underneath, but this one's a little bit simpler. This form here really begs the question, what happens if this interval gets arbitrarily large? Well, if it's arbitrarily large, nothing changes. Okay. But what happens if we could take this interval from minus infinity to plus infinity? Okay. What's going to happen, and we're going to do this, what's going to happen is, it's a little bit of a construction, but it's very, very natural. Basically, this integral is extended over the entire real axis, but you see you can't just set this in equal to infinity, so there's a little bit of a transformation involved. And this itself turns into an integral, okay? And that's a really useful and satisfying form when both of these, the coefficient and the function, are expressed as integrals. So we intend to do that as well. It's kind of staring us in the face, at least the idea. What's the question? What's going to happen? So I bring that up now. Other than that, I want to return to these. So in fact, I'm going to leave them up on the board and erase this. I'm going to return to these and discuss what they actually mean, okay, or beyond, what they mean beyond what we've already learned about. Good. So I will erase this and consult the clock here. It's a major topic, but we've got nothing but time. And the whole topic we will call functions as vectors. This is a section that builds right on what we've been doing. So we can always refer to this up here. And in fact, you know, I have to build one more thing in, but that's fine. So functions as vectors. So let's start with vectors the way we usually think about them. So we have R equals X, I hat plus Y, J hat plus Z, K hat, and we say that this is the X, Y, and Z, or these are the X, Y, and Z components respectively of this vector R in free space, X, Y, and Z axis. And you know, we could say we have our I hat, J hat, and K hat unit vectors. And furthermore, we have this I hat dot J hat is equal to 0, I hat dot I hat is equal to 1. I'm just going to write etc. Right? We have the orthogonality relations, and that these are unit vectors. Okay. So that's in free space. In an n-dimensional space, and still everything real numbers, we could have something like this. A equals the sum over A sub j x j hat. Okay, so now and j equals 1 to n. So that's a version of, I'm just using different names. So those are the components of the vector A from 1 to n. So in n-dimensional space, yeah. So, or we can write A is equal to A sub 1, A sub 2, all the way up to A sub n. And then x hat sub 1 is the n tuple 1 zeros all the way to 0, etc. Right? It gets a little tiresome to write all these things out, but you've probably seen this before. Unit vector, and you know, x2 hat would have the 0 and then the 1 there, and they are also orthogonal and normalized. So going back to this expression, we could say we have room right here. We would say x j hat dot product with x k hat is equal to 0 when they're not the same vector, when j is not equal to k, they're equal to 1 when j is equal to k. So yeah, this is an important thing here at the bottom of the board. Or we could say x sub j hat dotted into x sub k hat is equal to delta jk. And what this definition of this delta jk is exactly what I have right here. This delta jk is equal to 0, j is not equal to k, 1, j is equal to k, and it's called the Kronecker delta. Kronecker delta, so Kronecker was a mathematician. So, let's continue. So we'll continue with this because this is a nice compact notation. I guess I have to erase all these anyway. Okay. They'll be back. Okay, where were we? Good, so we have this vector, and you know, it's the components times the unit vector. It's exactly this thing here, except in n dimensions, and I'm calling them x sub j hat. I can name them anything. They are unit vectors. So in this example, the set of these x sub j hat, or let's not have to write that, we'll just write it out. The x sub j hat, just speaking of them as in plural, form an orthonormal set. Orthonormal set And orthonormal means orthogonal and normalized. In our case, we normalized to 1, right? The length 1. So when you have an orthonormal set of vectors, and those are our unit vectors, you can do the following. You can say, you can form the scalar product of your vector with an x sub, I need to use a different index, x sub k hat, and then since we have this sum here, a sub j, x sub j hat, we're going to dot that into x sub k hat, and that'll be the sum of a sub j, sum over j, x sub j hat dotted into x sub k hat, dot product. And there's that Kronecker delta, so we'll even write that just for the formalism, sum over a sub j delta jk. Well, there's only one of these a sub j's that's going to survive here, because this is equal to 0, jk, when j is not equal to k. So only that one survives, and that is equal to a sub k. Very important. So now what do we have here? We found that the a sub k component, the kth component of our vector, is just as the compact form for it is the vector dotted into or projected onto the k direction. Okay, projected onto the kth unit vector. Okay, it deserves its own box. And what I'm going to show you is that this, which is the basic structure of vectors as we've used them quite commonly, this structure here also holds for functions. And we've done it already because our Fourier series and Fourier series formalism has actually realized all of these properties. So let's look at that. Okay, I'm gonna erase it all now. But this all was vectors, and if I had added a little tiny title, obviously to realize this here, it was vectors and scalar product. So one, vectors and scalar product. And in fact, I should even add a note before I erase this. The assumption with these scalar products, the assumption with the normalization of a vector, giving it a length, has the scalar product built in as well. Okay. So the scalar product defines the length of a vector. So vectors and scalar product, and I'll even introduce this term right here, norm, and that's just a generalization of the idea of the magnitude. And we already know that the magnitude of R can be written as the square root of the dot product of R with itself. Okay. So those are all things we've used before, and in a sense I just made use of them here as well. Okay? Good. So that was our functions as vectors. I'm going to erase this and talk about the Fourier. Consult the clock. That was perfect. So this time I'm going to write down our Fourier series again, and what we'll see is that we have been using a scalar product and a vector space without even, a function space without even knowing it. Okay. So once again, the Fourier series, the Fourier expansion, we have f of x is equal to sum over c sub k e to the I kx minus infinity to plus infinity. So instead of 0 to n or 1 to n, right, I didn't write them out all the time, but I said it was n-dimensional. So here we have j equals 1 to n. I'm not going to write it down. You guys write it down. J equals 1 to n. Okay. Instead of that, we have infinite series and double infinite if you want, but that's fine. Good. And we're going to have c sub k 1 over 2 pi minus pi to pi. Leave a little room here. I actually got to write some words. I kx dx. Okay. Here's the thing. This we can think of as the vector. C sub k are the coefficients, and e to the I kx are the basis vectors. Okay. So here, f of x is a vector. C sub k is the kth coefficient, okay, the kth component of the vector is the kth component and e to the I kx is a unit basis function. Is a basis function. I'm just going to write is a unit vector. Okay. And how do I prove that? Okay. I'm just making the claim, right? I have some formulas, I'm saying this, that, the other. But I can prove that, and here's the way. We have to define, I'll stick with red, a good color. Proof, is this a proof? We're just going to call it a proof. Define the scalar product as, so instead of a dot, I'm going to do a f comma g. Okay, that's just like a dot b in our previous world. Okay, so f comma g is the scalar product, and it's defined as 1 over 2 pi minus pi to pi f of x g complex conjugate of x dx. So we're going to define that as a scalar product, and strictly speaking, we have to go back and peel and list all of the properties of scalar products and stuff. We're doing this the quick version first. So this is the scalar product for functions on the interval minus pi to pi. Okay. Scalar product for functions on minus pi to pi is just these two functions, f and g, 1 over 2 pi, f of x, g star of x is the complex conjugate of x dx. All we need. Yeah, we're actually going to peel out these formulas right here and erase them. So the first thing we do is work with these functions right here, okay? Let give it a name, phi sub k of x be equal to e to the I kx. So I'm defining it. K is an integer. This is our well-known function. Then integral phi sub k, oh, better than that. Then the scalar product of phi sub k, phi sub, in fact, let's use different letters. Phi sub m, phi sub n is 1 over 2 pi integral, so phi sub m is e to the I km. Now the n has to be done complex conjugate. So e to the minus I, hold on here, I m x, meaning e to the minus I n x dx 1 over 2 pi e to the I m minus n x dx. Okay. We've done this before. In fact, we did this integral when we invented it, right? When we came up with this here. So yeah, what is this? This is 1 over 2 pi times, if m is equal to n, then e to 0 is 1, integrate from minus pi to pi is 2 pi. So 2 pi comma m equals n. 0 if m is not equal to n, which we did in the past, and you should make sure you're clear on that, okay? Easy to do. So this, 2 pi cancels that one, so this is the Kronecker delta mn. And yes, these functions here, in terms of this scalar product, are orthogonal and normalized. Okay, so our e to the I kx, k is an integer, is an orthonormal set. I erased that, but I had it on the board, right? Orthonormal set. So now we can actually write, this is so great. So now that we have that, now write f of x is equal to the sum over k. I'll just even leave out the range, right? We know what it is. Sum over k, c sub k, phi sub k of x. Okay. And phi sub k of x is just e to the I kx. So I've just written down that Fourier series. And that c sub k, well, we have to pull one out, so c sub n is equal to, let's just do this first, okay? And f of x, I didn't have to write the x, and f comma phi sub n. So the scalar product of the function f with the nth, okay, with the nth, phi sub n, we're just going to use the abstract property here, is equal to the scalar product of the sum of c sub k phi sub k with phi sub n is equal to the sum of k c sub k comma phi sub k phi sub n. Kronecker delta kn summed over k is equal to C sub n. So if you look at what I did a couple boards ago with the vectors, right, with the n-dimensional normal real vectors, you will see that this just duplicates that formula. And now that we see that, replace n with k, and this here is that scalar product. Okay, so that's the meaning of the coefficient C sub k really comes out of a scalar product in a function space with orthonormal functions, orthogonal functions. Good. There's actually more to say about scalar products. I set it up here so that nothing wrong can happen. So because the scalar product is defined with complex numbers, you have to be a little bit careful. Okay. But we didn't do anything wrong. So we'll generalize that, but that's actually the meaning of this thing right up here. This coefficient is actually the scalar product of the function with basis function. And this is just one of the biggest things in theoretical physics. One of the real foundational things is to have function spaces, orthogonality, integration here. You'll see this repeatedly, and the best or the easiest place to learn it is here with the sines and cosines and the complex exponential, because we know them so well. Okay, I'm going to consult the clock again. This is close to where we're going to wrap it up. I'll put this in order and have the flow of the ideas. So first I have this as a scalar product, and then I apply it here, and just our old calculation we did at the very beginning of the Fourier section just shows that these things really do. In fact, we made literal use of this to construct this business up here. So yeah, this is just the structure of it. So now this function here is that sum. Different color, right? And the coefficient, as you can see from my definition of the scalar product, the coefficient literally here, the nth coefficient literally is just the scalar product of f with these basis functions here. I think that's where we'll leave it. We have a couple of projects to do with this whole complex of ideas. For now, it's good just to see it possibly for the first time. Okay, maybe I'll put well, I said it. You guys leave some room and fill in some words on what we just did here. Well, for example, I did this. So this is a basis function, which is to say a vector, basis vector, basis function. And then here we show that we have an orthonormal set. Okay. And this is the expression of, again, what we had up there. You guys maybe label it. Okay, this is literally that. And this here, read backwards, C sub k, C sub n, is this thing right here. But you'll notice, here's the thing. I didn't have to invoke this definition anymore. I really was just at the compact level of vectors, essentially. Okay, so that's why I left it in this compact form here. I could have reintroduced this, but we did that calculation already. Okay, good. We're going to leave it there. And hope you guys have a good break, and see you guys next time.